Now we're ready to get a little bit closer to the real world. We are approaching circuits. We are approaching circuits at a glacial pace here. Let's ask ourselves, what would it take to make a current flow in this piece of a conductor? There it is. Conductor, free electrons are ready to move. We just got to make a current flow. Well, that's why we introduced the idea of potential difference. Like I said, potential is an energy. It's a way we describe electrical energy. It's what we use to make something, to make current flow. So the way we do it, of course, is with a power source, right? So for a lot of circuits, that's a battery, or for others, it's power supplies you plug into a wall, which is getting the power from somewhere else. But for little lectures and demonstrations and thinking, we like to play with the battery. So a battery is a little box, and inside are some chemicals, and the chemicals are carrying out a reaction that holds the two electrodes at a set potential difference. Okay? So what I'm going to do now is just draw the battery like this. Here's the top of the battery, and I always forget which one is positive and which one is negative. So we've got a little bump here, and then here is the big one that takes the thing like that. There we go. And this one is positive, and this one is negative. And the battery says 9 volts. And that is the unit of the potential difference, which I think I forgot to tell you in that previous lecture. So potential difference comes in joules per coulombs, because remember, we had that V was U over Q. So that's the joules per coulomb, or the name for that is the volt. Okay? So 9 volts means it holds this electrode at 9 volts higher than that electrode. Or if you prefer, you can say this one is at 0 volts and this one is at 9 volts. But remember, it's always a potential difference. You could also say this is at 10 and this is at 19. Really all that matters is one is 9 higher than the other. Okay, but by convention, we usually make this one 0. So we can call this one 9. Okay, so there we are. We have a potential difference. What we got to do is apply it to the conductor. So we're going to connect it with what we call a conducting wire. So this is something that just carries the current. So I'm going to connect it to that half of the big conductor, and I'm going to have another wire coming to this half and touching the 0 volt electrode. Okay. So now this 9 volts is being applied here. We could say this is 9 volts. And this 0 volts is being applied here. The other end's at 0 volts. So now we have a potential difference across the conductor. This is at high potential and this is at low potential. And that's what makes the current flow. You could almost even, if you wanted to physically be able to think about it, what we've done is it's kind of like we've put a giant positive charge here. Remember we calculated, or I gave you the potential near a big positive charge. It went as KQ over R. It went down as 1 over R, right? So when you get really close, it was really big. And as you move farther and farther away, that potential comes down, 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 down. So up here is 9 volts, and down here is 0 volts. If you had a positive charge sitting here, it would be repelled by that big Q. We don't really have a positive charge sitting here, but we do have the potential going down, which is really the same thing. This creates a potential that goes down this way, but another way to do it is to stick a battery on here that creates a potential that goes down this way. It goes from 9 volts to 0 volts. So all we got to do is realize there's little positive charges here, and they're feeling a force, and they're being caused to move that way, like that. Except, are there really little positive charges moving that way? I'm taking the blue pill, and I'm going to say that there are positive charges moving that way. You know that there's really negative charges moving the other way. But we define the positive charges to the right. Therefore, we would say there's a current flowing to the right. Okay? So what have we done? We applied a potential difference, delta V, to a conductor. Okay, and what happened? Charge flows, positive charge flows, and we got to be sure we get the direction right. It flows from high potential to low potential. Okay? You can always remember that. Well, one, just remember it. But two, a positive charge would flow from high to low because it's going away from the high potential towards the low potential. This is like the more positive end. This is like the more negative end. So a positive charge will be repelled by the positive and attracted towards the negative. Okay, so it'll go like that. And then the final question would be, how much do you get? Do you get an amp, 10 amps, 20 amps? If you have 9 volts here and you got a piece of conductor there, how much current does it cause to flow? And the answer is Ohm's law. Ohm's law is an equation that tells you how much you get. And the answer is delta V. If you apply a potential difference, delta V, you get a current. This is in volts. This is in amps. And times the resistance of the conductor. Any little object you flow stuff through has something called a resistance. And this is in ohms. And we are going to be talking a lot more about resistance. But basically, Ohm's law is telling you is that every object has this property called resistance. And it defines how much current you get per how many volts you put across the object. Okay? And I'd like to take a minute to point out that this is a horrible misuse of the word law. Okay? You're taught in grade school that in science something is a theory, and then they do a bunch of experiments, and if they prove it, it becomes a law. It's almost the opposite happens. It's almost the exact opposite in recent times. This is not a law of the universe, Ohm's law. This is just materials kind of tend to do this. They don't actually really do it perfectly. Semiconductors don't do this at all. Okay? If a material warms up, you get deviations from Ohm's law. So Ohm's law is really just sort of a general way that materials behave. It is not a law of the universe. Other laws of the universe are still called theories. General theory of relativity, that's not a theory, that's a law, right? So don't get too hung up on law and theory like I am, okay? Anyway, we'll be talking a lot more about resistance.